Welcome to another big session. This time it'll be a Mathcad for structural engineers. First, before we get to the Mathcad, a reminder of the Daddy Pig YouTube channel. And while you're here, why not click on that subscribe button and click on like, send me a comment, why not? Okay. So on with the show. So today's exercise was to update this particular document, and it's the roof bracing for a small building and using PIR panels, roof panels. And it's loosely based on NZS 3604. Now, we were asked to do this, and the fee for it is quite small, so I thought I might as well make an exercise out of it. Because the original of this was done over 10 years ago, we've probably lost the original calculations. At least I couldn't find them in the archive. So we've been issuing this document for many years, and we have nothing behind it. So me being me, I said, well, let's do a few calcs. How hard could it be? So the intention is you're a small building, and we've put limits on the roof diaphragm of 15 meters by 7.5 meters with a maximum roof pitch of 25 degrees. So what do we do with our Mathcad? So here is the Mathcad. We're using the insulated panels as a ceiling diaphragm. And the trick to it is actually fix it all the way around. So we're not showing the side walls, just for clarity. So first of all, we need to put in the height and the width. And by default, our length has just doubled the width. We've got a range of roof pitches. So I immediately started by putting in an array here. So I've got values of roof pitch from 5 degrees through to 25 degrees, which makes the height of the high side basically from 3.65 meters to 6.497 meters, which means our average height for the purposes of calculating the wind load is from 3.3 to 4.7 meters. And similarly, our roof length is worked out from 7.5 meters to 8.275 meters, depending on the roof pitch. Now we have a table, and we're going to use NZS 3604, the basic wind speeds it gives there. And they have wind speeds ranging from low through to extra high. And the wind speeds of the site beta ranges from 32 meters per second through to 55 meters per second. That translates into a pressure of 0.61 through to 1.82. So it's got a big difference in there. So by the way, if we're beyond the extra high, we'll be looking at specific engineering design. So from my table, which you can cut and paste from your reference document, and you can take that and create an array, this time a vertical array, of the wind speed and the wind pressures, which we will use later. So we've got wind pressure coefficients taken from NZS 1170.2. We've got a windward side 0.7, a leeward side of -0.5. And we've got upwind suctions, which vary from a -0.9 through to a -0.3. depending on the roof pitch. Now we'll conservatively put the combination factors at 1 and the area factor at 1 and the porosity factor at 1. And we're just looking at not the local loads, but the general loads without an additional local wind factor. So now we multiply all those together, and we get the lateral wind load on the top half of the long walls. So this is the overall wind load on the little building, and it's applied to the walls, but we want the reaction at the top of the wall. And we're going to take the average. We're cheating a little bit here, but it kind of works out for spreading our wind load. And that comes out from low to extra high, and then from 5 degrees all the way through to 25 degrees. You also have uplift on the roof, which is what we're concerned about here. And as you increase the angle of the roof pitch, the actual uplift actually decreases. So going from, again, low wind to extra high wind, and from 5-degree pitch to 25-degree pitch, we get our wind uplift measured in kilonewton per meter. And that's assuming that the roof panel is simply supported. So you're just taking the reaction on one side. Now, in some cases, the roof panel won't actually span the 7.5 or 8 meters you need for that. So you may need to put in intermediate supports. But for the purposes of this exercising, I'm assuming it can, because that's how you derive the fixing loads. Okay, so this is what the diaphragm looks like on plan. This is the roof. So our length is down one side and our width is down the other side. And when we apply our wind load at the top of the wall, we create a bending into that roof panel, and the diaphragm action converts into a tension and a compression. And the tension and compression are equal and opposite. So the shear on each side is basically half the load. So we take our wind load on the top of the walls, multiply by the length, and divided by 2. And so we've reminded ourselves of the wind zone we're in, low to extra high, and the angle of the roof going from 5 degrees to 25 degrees. And this is the shear in kilonewtons that we get as a result of that, ranging from 9.1 at one extreme to 38.9 at the other. The wind also develops a bending moment in the roof panel, and again, we're assuming that the roof panel is simply supported, which is a bit of a cheat, but why not? And because of that bending moment, you get a tension and compression. We're putting as equal and opposite, and that again is just the moment divided by the width. We're saying our fixing spacing is at 250 millimeters, which coincides with the space between each rib for this profiled roof section. Our shear on the fixings in the short wall due to the roof diaphragm action, take our VIR and multiply it by the spacing. So this gives you your shear on the fixings in the short wall due to the roof diaphragm action. You're taking that V, that shear, and dividing it by the length of that wall. Then you get the shear on the fixings in the long wall due to the roof diaphragm action, and this is where the T and the C come into it. And you're cheating again a bit, because that is divided by half the length, because you're developing that tension force between the roof diaphragm and the wall. Then you get shear on the fixings in the long wall due to the wall loading. Actually, this is the loading on the wall that's transmitted to the roof. And it's the wind applied to the top of the wall multiplied by the spacing of the fixings. To work out the vector sum, we need to summate both of those values on the fixings on the long wall and then square root it. So we do that in 2 stages, square each of those values and then square root the lot. And that gives you the vector sum, and I've called it V-des2. And this V-des2 actually exceeds V-des, which means the shear on the fixings on the long wall exceeds the shear on the fixings on the short wall. To complete, we've got uplift on the roof, so that puts tension in our fixings, and we multiply that through, so we get from 0.52 all the way up to 1.54, depending on the loading we've got, going from low wind zone to a extra high wind zone. Okay, so that's the roof and that's the loads. Move on to the connection design. And this is the typical connection design we have on an insulated panel roof when we screw it into a timber framed wall. So we have a piece of timber wall head and a through screw through the panel into the timber. And the capacity of the screws in the steel skins we need to check. And we've picked 14 gauge tech screws, and that nominal screw diameter is 6.3 millimeters. Again, our screw spacing is 250. The thickness of the material, it's steel, so it's 0.59, both top and bottom skins. And the tensile strength of the sheet is 340 and the yield strength is 300. So you're looking at grade 300 steel for both skins. The main issue will be tilting and hole bearing, and we're using this equation here from ASNZS 4600, which is our code for light gauge steel design. And our design bearing capacity works out as 1.41 kilonewtons. There is another equation which doesn't actually apply because we're really only looking at the top, which is directly under the screw, because what you're fixing to is the timber, which is underneath. The extra factors for VB2, for the second skin, takes into account this 4.2 multiplied by the square root of the cube of the thickness, but that's the second thickness, so it's not particularly relevant here. I'm saying that the load is shared by both skins, and so the applied load of V-2 is then divided by the capacity, which gives us our utilization ratios for the screw through the panel, ranging from 12% to 51%. So that looks okay. Now we need to look at the pull out and pull over. Well, it's mainly pull over for this because we're looking at the top fixing. And we've said we've got again, 14 gauge screw, so the diameter is 6.3. Our head diameter, we just made it double the screw diameter. We've allowed a 16 mil diameter washer, and a thickness, we've just taken the minimum. The thickness is T1, T2, we've taken this 0.59. So the pull over diameter effective is going to be 15.73. This is taken from ASNZS 4600. So the design pull over capacity, once we've applied a strength reduction factor, comes out as 2.367. And again, our load is not shared by both skins. It's actually shared only by one skin. Change that. So we've got our pull over capacity and comparing it to the tension we get from the wind uplift. And we find that our minimum utilization ratio is less than 1. And we've got to say it's greater than -1 here because we're looking at negative numbers because we've got wind uplift. Then we look at combination in accordance with clause 5.4.3.4. And we just simply take one from the other because half of them are negative. And we work out that we're more or less okay because it does allow you a 1.1 factor together. Okay, so the next stage is we're looking at aluminium because we were asked to look at structural insulated panel with aluminium skins. And we've chosen a 0.9 millimeter thick grade of aluminium. The grade is 5005-834, which is a typical sheeting grade rather than a structural grade. And our thickness, as we said, is 0.9. The bottom and top are going to be the same thickness. Our screw diameter, again, is 6.3. There's 14 gauge screws. Our yield strength is 103 and our tensile strength is 138. But when we're calculating the capacity and shear of the fixings, we need to know what the bearing strength of the skin is, 276, and the bearing yield as 165. So taken from clause 5.3.2, we work out that our capacity is 1.78 or 2.2. So we take the smallest of those two and then apply a strength reduction factor to give us a design shear strength. and of 0.889 kilonewtons. And again, the capacity of the lower level T2 doesn't apply here because there's a similar clause in AS and Z 1664, which puts on a limitation on the lower fixing capacity. And we're saying that the load is shared by both skins. And so our utilizations range from 19% to 82%, depending on whether we're going from low through to extra high wind. So those are all lower than 1, so we're okay. Now, we're looking at tension, and the tension capacity is, in this case, the pullover. And you're looking at a washer head, in this case, 30 millimeters. Now, strictly, the code doesn't allow you to do that, but because we're using load spreading washers, we're effectively using the washer diameter, the load spreading washer diameter, as the head diameter, which gives us a pull over force of 1.74. And that works in most cases apart from the extra high wind. So we think that these panels in aluminium should be limited up to the very high wind rating. Okay, so we're fixing our roof panel to a timber framed wall, and so we have a timber wall plate, and we need to know what the screw capacity is there and if we're still under it. So we have, again, our screw diameter is 6.3 because it's a 14 gauge screw. We're looking at short duration wind loads, that's K1 is 1, and we're looking at dry timber, so K12 is 1. Strength reduction factor in this case is 0.7, and we've only got one of the screws, or we're saying there's only one screw in the shear plane. So we get a characteristic strength in shear, it's taken from table 4.5, that's 2.6 kilonewtons, and the design strength of the joint is that multiplied by the number of shear planes and the K factors and the strength reduction factor. That gives you a utilization ratio varying from 18% to 78%. Okay, and the final thing is to look at the joint capacity in tension. And we look at the tension screw penetration of 35 millimeters. That's a typical penetration into timber from our panel fixing. We take our characteristic withdrawal load from NZS 3603, table 4.6, 4.7, and equation 4.6. That works out as 2.78. Once we apply our strength reduction factor on it, we get utilizations varying from 27 through to